Thank you very much. So that's actually a pretty good segue into where some of this presentation will ultimately go, given you'll see. So what I want to talk about is a sector which is a very strongly growing sector, forecast to double or triple by the middle of the century in terms of passenger kilometers traveled, and that's aviation, which serves to connect the world. Many of us in this room probably wouldn't be here if it weren't for this industry. So it's sort of one that I believe is a cultural good. It connects the world, provides economic opportunity, and something we want to expand the opportunities it provides to more and more people. Of course, the downside is the environmental challenge. So we need to reconcile the huge economic and cultural benefits of aviation with the environmental challenges it poses. And as you can imagine, flying a several 100-ton vehicle at 1,000 kilometers an hour through the night to get you halfway around the planet is a somewhat energy-intensive and technologically impressive thing to do, as well as organizationally. So how do we get to zero environmental impact aviation is the question. Well, I'll start by specifying the causes of the impacts of aviation, focusing on climate change and air pollution. So there's really four kind of emissions that really matter. CO2, which you all know about. NOx, that's oxides of nitrogen from burning hot in air. Contrails and contrail cirrus, which I'll get to later, that's unique to aviation and makes it a bigger challenge than it otherwise would have been. And then sulfur and fuel, a relatively minor part. So let me put this on a common scale of dollars of environmental impact per ton of jet fuel burned. And that helps sort of prioritize which things matter. And by the way, there's sort of a list of another page of emissions that you could consider, but they all come into very small slivers on this sort of chart. So what you can see here is that really the climate impacts come down to two things. CO2, which is what you'd expect, and then contrails, which I'll get back to in a moment. Now, this is one particular estimate from MIT. There are different estimates that say that the contrails part might be double what it is here. So if you're to have a mental model of what are the climate impacts of aviation, it's roughly half CO2, half contrails, everything else comes out in the wash. And there's scientific debate about that, everything else and so on, but roughly that's the simple model. Now, as well as climate, we also care about air pollution and human health. And if you put on a dollar basis the human health impacts, then they're not negligible compared to climate. Estimates vary again. They could be smaller than climate. They could be more. There's uncertainty as always, but it is clear that it's an important consideration. In this case, NOx is really the first order thing, and nothing else matters very much. So that means basically we have to eliminate CO2, eliminate NOx, and somehow deal with contrails. So contrails, this is what they are. Half of the warming from aviation. If you think about the sort of physics of it, they're suspensions of ice crystals in the atmosphere that are formed because when you burn a hydrocarbon fuel, or hydrogen combines with oxygen in the air to get H2O, so water, so you're emitting a load of water. If the atmosphere is cold enough and humid enough, which happens about 7% of the time, then all that water freezes onto soot being emitted from the engine and creates these line-shaped ice clouds. So it forms around 7% of the time, but causes about half of the warming from aviation. Now, what about how big is this at large scale? Well, until now, really only modeling has told us how much contrails matter. But thanks to a new satellite asset that NASA launched called the GO satellite, combined with deep learning now becoming very routine to apply in many applied areas of research like this, we're able to take the satellite images, process them through a deep learning algorithm, extract all the contrails viewed on the satellites for 2 years, and then plot an annual average image of contrail coverage over the United States as viewed by the geostationary NASA GO satellite, which is viewing 24 hours a day. So something about this is that the deep learning algorithm used to identify these contrails doesn't know anything about airplanes or where they fly. All it was trained to do is identify contrails. And what you can see here, and when we show this to flight dispatchers and air traffic controllers, they say, well, I recognize these patterns because that's where planes fly. So that's sort of some level of validation that what we're seeing, which shows up visible from space, is actually related to aviation and not a natural phenomena like a cirrus cloud. Now, a second thing that probably you will have all started to think about and you'd think of it pretty quickly if you put your mind to this is, well, of course, COVID flights went off a cliff early on in the COVID pandemic. That's a natural experiment, right? And you'll definitely be right at that. So we were able to leverage that and apply the algorithm to sort of minute by minute, every 10 minutes by 10 minutes through the year in 2019 and 2020. Now, I don't know about you, but I sometimes forget which year did COVID even start, and it's kind of a bit of a blur, so I might have to remind you. I got this wrong when I gave this presentation or this slide a few days ago. So 2019 was a normal year, if you remember whatever normal is now, I'm not sure. And then 2020 was when COVID hit, and COVID hit around this dashed line here in March. So what this is showing is the blue line is a normal year, then the red line is the COVID year. And as you progress past, let me see if the video will play again. Oh well, the video doesn't seem to like this computer. Anyway, as you progress past March, you can see that or maybe you could see that. You can see that the blue line, which is 2019, which shows the coverage over the United States, starts being much higher than the red line, which is the coverage during the COVID year in March when the pandemic really started hitting. So it's sort of a very convincing demonstration that contrail coverage is related to aircraft activity and isn't a natural phenomenon.
Give me 1 second.
Yeah.
I'll get it for you.
So anyway, that sort of gave us a lot of confidence to say two things. First is we really are sure that contrails are real and verified. It's not just models, and you need more than models really where possible. Like with CO2, you can measure it and verify it and things like that. And contrails now we can do that at large scale. And the second thing when you look at this is that you start thinking, well, this is actually real time, right, or close to real time. We have images taken every 5 to 10 minutes. They get downloaded from the satellite within a minute or two. We can process them through deep learning within a minute or two. And so sort of from satellite image to having useful information would be something in the low tens of minutes, maybe 10 or 20 minutes. Now that's not quite real time as such, but if you think about the lifespan of contrails, which is up to 6 hours, if you can see a contrail forming in a certain region within, say, 10 or 15 minutes, and you can avert the remaining several hours of its lifetime, and then know that's a contrail forming region, then what you can start thinking about is doing contrail avoidance in real time. Now, in particular, I mentioned contrails only form perhaps 7% of the time, and they form in regions of the atmosphere that are vertically very thin and laterally very wide. So they're like pools in the atmosphere. So what this is enabling us to conceive of doing is, in real time, watching flights with satellites, identifying the contrail-forming regions, and routing the planes essentially under those regions, which is the most efficient thing to do. So we're now sort of contemplating potentially experiments and things of that nature, and perhaps you'll see announcements about that in the future. But it looks like a very promising approach. Now, of course, you might say, well, what's the cost? And it does have a cost. And in particular, the cost might be something like 1 to 2% of additional fuel burn. So averting roughly half of climate change from aviation in exchange for 1 or 2% extra fuel burn. So that's probably a very good deal. And in particular, we think it's the cheapest and fastest way to mitigate the climate impacts of aviation, because the alternative I'll get to next is a very important thing to do, but it will be a much more expensive thing and a much longer term thing to do. So that's contrails. Now, what about CO2? Well, for CO2, the near-term option is called SAF nowadays, Sustainable Aviation Fuel. You may have heard of it in the past being referred to as biofuel. The idea there is that you grow some kind of crop, could be switchgrass, could be some woody biomass. As you grow the crop through photosynthesis, it takes carbon out of the atmosphere, and the physical crop itself is made of carbon and other things. You convert that into a hydrocarbon fuel, which is maybe 86% carbon by mass. Then you burn the fuel, and you return the carbon back to the atmosphere, so in theory it's closed loop. Now in practice it won't have escaped your attention that a tree or grass doesn't look much like jet fuel, which is a tightly specified safety critical transportation fuel. So it's not surprising it takes a bunch of energy to convert the biomass into the tightly specified safety critical fuel. And so that means that you don't quite get zero carbon in total. In addition, there's a whole range of issues related to land use change and competition for food and things like that that have to be thought about. And that's kind of a large area of work in the lab I direct, is evaluating all the different kinds of fuels you can make that are in this category called SAF, or Sustainable Aviation Fuel. And we produce things like this chart here, which shows the carbon intensity in grams of CO2 equivalent per megajoule, so thermal energy from combusting the fuel. And that's compared against the red line on the right, which is the fossil fuel baseline. So you can see different fuels have different life cycle carbon intensities, but it's clearly very possible to have a range of fuels that gives you very, very significant reductions. Reductions that could come online for existing airplanes, existing engines, existing refueling infrastructure, and faster than you could introduce a magic new plane that is going to reduce emissions by 100%, which is going to be a technological challenge, to say the least. So SAF is an important part of the future for aviation in that it reduces the life cycle carbon dioxide emissions, but it's not the end of the story, because basically there isn't enough available land to grow enough or to create enough SAF to fulfill the needs of the industry. Now there's a range of estimates you can come up with, and we've done analysis where we look at every parcel of land in the world and every fertilizing scenario and water irrigation scenario that you could think of, and then a range of policy scenarios of how much land you could really take for creating SAF. Now, that gives you a range of things as you might expect, but the thing that is clear is that there isn't really a realistic scenario that gets you to 100% for aviation as it looks in, say, 2050. Numbers like a quarter might be more realistic. So, you have fossil, you don't want to use fossil fuel in the future. You have biomass, that's important and a great start, but there isn't enough biofuel or SAF. So what else is there? Well, we can't carry around fusion reactors because they're too heavy, obviously, and we probably wouldn't want to carry around fission reactors. So the only thing you have left is using electricity somehow, and ideally green electricity. Now, that's just by elimination, unless anyone has another idea. So that means you need to get electricity to power the plane somehow. Now, people like Elon Musk will say, well, you'll have battery-powered VTOL supersonic aircraft in 2023. I hope so, but that doesn't look tremendously likely based on the analysis that many people have done. And it really doesn't look that viable to have large and long-range battery-powered aircraft. So that tells you you still need liquid fuels, or at least liquefiable fuels. And then, as I previously argued, you don't want fossil, you run out of biomass, all that's left is using green electricity. So in that sense, the future of aviation is electric, but not in the Musk way of colossal batteries, but electrofuels or power to liquid. Now those fuels could be synthetic jet fuel, looks just like jet fuel, or it could be hydrogen, or maybe even ammonia, that's more suitable for shipping than aviation, and possibly other options. So overall then, the future for aviation fueling, I think, looks something like this. Fossil fuel now, transition to drop in SAF or biofuels as fast as economically viable. Eventually the biomass maxes out, so you start needing to create electrofuels or power to liquid at large scale. Now initially you definitely want to do that. That's in a way that's drop in, so synthetic fuels that go into existing airplanes and infrastructure. And you might say eventually, well, what about hydrogen? Now, hydrogen isn't an either or because you need vast amounts of hydrogen to make a hydrocarbon fuel. So in any event, making lots of hydrogen from electricity is inevitable. The only question really is how do you use that electricity to make just hydrogen or to make a hydrocarbon fuel? Well, the arguments are kind of more balanced than you might imagine. A hydrogen plane isn't in any sense magic, and it's not really a whole lot better, if at all, than a synthetic jet fuel powered plane. So they put some numbers in that to the extent we have analyzed it at this point in time. If you create an electrofuel, which is a synthetic drop-in jet fuel, that might cost you 1/3 more electricity than making hydrogen per unit energy of the fuel you're creating. So it's cheaper to make the hydrogen fuel than the synthetic fuel. So on that basis, you can say, well, let's go for hydrogen. However, the hydrogen plane will be bigger and heavier and more draggy, and so we think it'd probably require about 17 or 20% more energy. So of that 1/3, you've lost, let's say, 20%. So now you're down to, creating the hydrogen airplanes, creating all the infrastructure to go with it, and all you've got is a 10% prize. I mean, that's not a huge prize to go after. So it's in the balance. Then there are other issues like hydrogen probably creates more contrails because there's more water vapor emissions. That could easily eradicate the benefits and turn it negative. So you could in the future decide to go to hydrogen because there's that 10% prize to go after, and that might make sense in some cases in some regions. But there's the downsides, and it just might not be worth it. So it's kind of a balanced thing that we'll see how it evolves. But there's not a massive win to be had there. And then finally, all of this is based on electricity in the future. Then you might say, well, if you can invent a battery that really is high enough energy density by unit mass, then in the long run, at some point in the future, you go for battery. But this isn't really as binary as some people portray it, right? All of the stuff early on is about moving to synthetic drop-in fuels. Then you have this overlapping phase, which is all about hydrogen. You need hydrogen for the biofuels. You need it for the synthetic fuels. You'd even need it if you want pure hydrogen. And then all of it's about electricity, and it's just a case of what the carrier is. So it's really a continuum over time that would have phases to it. So, by the way, how long do I have left? It's 8 weeks, okay. Okay, thanks. So just to put a couple of numbers on it to give you a sense of, would this be 100 times the price of today or something like that? And I'll just choose hydrogen as an example. Now these numbers on the right here give you the cost for producing hydrogen, and then there's a jet fuel energy equivalent, which is the horizontal dashed line. So you can see from that there's a bunch of ways to create hydrogen. They result on the left, you can see different levels of greenhouse gas intensity compared to the jet fuel number and the green dashed line. And they're more expensive than jet fuel, of course. But they're not 10 times more expensive. They might be 2, 3, 4 times more expensive. Now, 2, 3, 4 times as expensive today sounds bad, but in 20, 30 years, you'd expect the world to be n times richer, right? So the sensitivity to prices will sort of change in such a way that a 2x or 3x or 4x increase in the fuel price, which might be today it's maybe a third of the operating costs, won't be the end of aviation. It won't grow as strongly as you might hope, but it'll be very much a survivable change. And indeed, in the past, we've been in a world where fuel cost twice as much as today, in a world that was then poorer than it is today. So obviously, you would hope you can make the fuels cheaper, but even if you can't, it's still a viable future for the sector. It's just one where the fuel might be more than a third of the operating cost. It would be a higher percentage. And then if you take one interesting example, is this one called BECCS. This is bioenergy with carbon capture and sequestration. This is quite a cool one in that it means you make a fuel you can sell and at the same time sequester carbon. So the idea is grow the biomass, burn it to create electricity, sequester the CO2 that comes from burning it, and then you make hydrogen from the electricity. And this is an example of a carbon negative fuel where you see the green line is strongly negative, and then the cost is roughly 4 times jet fuel today on an energy basis. So it's not ridiculous, but it does have some cost pain, and research will help reduce that. So finally, then I wanted to mention the other half of the environmental challenge, which is air pollution. So climate was really about CO2 and contrails. Now, in the case of air pollution, I mentioned that NOx is the big thing for aviation, like many other sectors. And if you think about trucking or ground power generation, for 20 years we've had the solution, which is really looks like this. It's using an ammonia-based solution with a SCR, a type of catalyst, to reduce the NOx. And this is a well-established technology in trucking and things like that. So could you apply it to aviation? Well, historically, you would have thought, let's take a 1960s turbojet engine where all of the air going into it goes through the combustor, becomes polluted, and comes out the back and is the thrust. If you put an emissions control system in the back of that, that might drop 10% of the thrust. That probably would be crazy. Right? But if you think about a modern engine has a bypass. So you see the engines are really big now, and they have this small part in the middle called the core, which is where the fuel is burned. So roughly 10% or less of the air going into the engine goes through the combustor, has fuel added and burned, and comes out the back. And 90% goes through this bypass duct, which reduces 90% of the thrust. So now if you take that same mental model and put an emissions control system in the back of that causes a 10% loss of thrust, you're causing a 10% loss of thrust on 10% of the thrust. So that's a 1% loss. And if you could eliminate the NOx in exchange for a 1% loss of thrust or increased fuel burn, that sounds good. Of course, you wouldn't really stick an emissions control system in the back of an engine. It would look different, and this is how it might look. So in this concept, you have gas turbines in the fuselage of the aircraft. You have them powering electric generators, which electrically distributes power to electric fans, which are more distributed for greater propulsive efficiency. And then the effluent of the gas turbine goes through an emissions control system, which is folded up in a way so you can get a large area inside the aircraft, and then you emit the cleaned air. So that's sort of the concept we've been looking at. And our first analysis of that suggests you could get a 95% reduction in the NOx emissions. So for practical purposes, it eliminates the air pollution in exchange for a 0.5% increase in fuel burn. And if you're using a SAF, then you wouldn't have an increase in CO2 or very small. So to summarize then, I think the path towards zero impact aviation is actually becoming clearer. It's expensive and challenging, but it's physically possible at least, which wasn't obvious, they say, 5 years ago necessarily. And the elements of that are contrail avoidance to avoid the roughly half of the warming from these line-shaped clouds that gradually become cirrus clouds. Secondly, fuels, so sustainable aviation fuels from biomass, and then electrofuels or power to liquid and various names. Third, electrification both of the fuels and potentially of the airplane, and that can be an enabling technology for emissions control, which can get rid of the NOx. So thanks all for your kind attention, and happy to enter into any discussion in the time we have left.
Any questions?
Thank you. In terms of the NOx reduction, how expensive, or what do we know about the expense of developing those technologies?
Very little, to be honest. It's relatively early, and we're just starting to work with a major engine manufacturer on working up the concept. It's not going to be cheap, but it probably isn't going to be significant compared to the cost of the overall airframe. More likely, the real cost would be reconfiguring the entire aircraft in such a way that it could accommodate that, and that would be billions of dollars, because this wouldn't work in an existing configuration, essentially.
Very interesting. So I don't know anything about aviation, so maybe this sounds naive, different eyes. So maybe I spaced out on the contrail. So you're saying it only happened, it's 7% of the time, but 50% of the impact. You're using the satellite to adjust the plane's route so that it's not in that. So couldn't you put like a vision system on the back when it sees a contrail, say go up or down, and then some algorithm tells it to do something, or is that way too simplistic?
Well, yes and no. So actually, there was a patent filed on that very idea by now passed away German scientist who thought of that in the 90s. And it would actually work at some level. The thing is, there's a technicality I didn't go into, which is that maybe 20% of the time you form some form of contrail, or more than that. It's just that contrail is non-persistent, so it never freezes. It stays as water and evaporates. Whereas the ones we care about are the ones that create the contrail for several plane lengths, and then eventually they freeze. And when you look out the back of the plane, they look the same. So the problem is you just wouldn't really be able to tell from looking out the back of the plane. Having said that, having airborne cameras and even ground-based cameras would all help, because you could sort of fuse all the data and figure out a more complete picture. But just the backwards-looking thing alone probably wouldn't quite give you enough information to really know if it's persistent. And the downside of only using that is you probably you'd do way too many diversions, because you'd be overestimating the contrail formation. But yeah, at some level it would work and be useful.
So I'm not that crazy.
No, it's,
right.
or no more crazier than the rest of the people working on it. So.
Okay, thank you very much, Professor Barrett. So